I'm Daniela. I'm a principal software engineer at JP Morgan. And today I brought you, with pleasure, this talk called Fun with Generics, which I consider to be the third and final chapter of my trilogy of fun with talks. Of course, this has become like even bigger. We have a spin-off now that Bets present today, like fun with data structures and algorithms. So yes, if you haven't the opportunity to watch her talk, please watch. And the first talk in this series was fun with pointers that I present here in Gophercon 2019. And then I present fun with slices earlier this year at Gophercon in Japan. And now, final chapter. So if you're curious about the other episodes, go to YouTube. Clicker. Thank you. OK, so this is me. This is just in case you find me outside, you want to talk about something else that's not generics. So I'll give you a bit of ideas for a conversation. I'm Brazilian. I'm living here since 2019, so about 4.5 years. I have way too many years of career, did a bunch of stuff, software engineering, DBA, sales engineering, data engineering, consulting. Now I'm a software engineer again. I'm a cat person, not a dog person. I love dogs, but cats are better, sorry. Bunch of hobbies, video games, anime, kendo, Japanese, da-da-da. And the most important part is, even though I'm here, I'm an introvert. So that means if you leave me outside, I'm not going to initiate a conversation, so come to me. It's better, trust me. Otherwise, I will be alone. OK, there's now the disclaimer part. No production code was harmed during the making of this talk. This is highly experimental. Like, this is generics. I'm trying to I have actually a confession to make. Everyone that knows me for a bit more time knows that I hate Java. I absolutely hate Java. But my guilty pleasure is Scala. I had an opportunity to work with Scala when I was a data engineer, Apache Spark, and I like the functional aspect of it. So we're going to uncanny valley territory here, because I'm going to try to bring some stuff from Scala to Go and see what happens, and see if it breaks. OK, but no code so far was harmed in production, and please, after this talk, I hope to continue that way. Of course, I'm not sure if everyone here is familiar with generics, so we're going to do a bit of leveling up. Then we're going to talk about Monads, which is the thing I decided to use to implement in Go, and then we're going to answer this question: can Go do Monads today? Of course, the internet doesn't allow us to forget. So this is a post that was made on the Bird app. I did this 2 years ago on Gophercon 2021. I did an interview with GoTime, and they asked the question, what's your unpopular opinion? My unpopular opinion was, sorry, guys, Go doesn't need generics. And of course, the key word here is need, because Go was mature by then, like 10 years old. Without generics, it was working just fine. We built plenty of stuff there. But now that we have generics, yes, I'm guilty. I'm using it. So this is previously in Fun with Slices. Yeah, imagine that flashback in the beginning of the episode. Said, yes, I used it. So what are generics? This is kind of everyone talks generic. Well, but what is this? It's kind of like everyone knows what it is, but it's kind of hard to define. So I tried to come up with a definition that wouldn't offend everyone. And this, my definition, a language feature that allows developers to write code that doesn't have hard-coded types. If you're old enough to remember C++ and templates, we used to call this meta-programming. And the important part is that the heavy lifting is done at compile time. So you write code for the compiler to generate code for you. Before generics, this is an example of the standard library package sort. You tend to do stuff like this. I have my type. I need to say, oh, this is an int slice because this is a slice of integer. This is a string slice because it's a slice of strings. Oh, this is a sort function that operates on ints, and a sort function operates on string, and so on. And the fun thing is, if you want to do something generic, like to sort, you need to start thinking about interfaces. And when I look at this, I was super surprised to see this in sort package, because I don't know if this is brilliant or horrible or both, but the more I look at it, I think it's brilliant, because sort package has an interface called interface. And I thought it's kind of like calling a package or a struct. But when you think about sort.interface, okay, yeah, it kind of makes sense, but it took me a while to process. Nowadays, by the way, we have a better way of dealing with this. Like if you paid enough attention to the Go 1.21 release notes, you have a slices package, which they describe as a more ergonomic way of doing sorting. I love this expression. And basically, now we can write stuff like this. Instead of hard coding the type, like this is a slice of int, this is an int slice, we can use this type parameter expression to say, okay, I can operate on types t, and I'm going to replace t later, right? And you can have a bunch of type parameters here. It doesn't need to be just one. You can have, like, in this case, 2. In this case, e is a comparable type, and s is a slice of e. Let's decompose this a little bit further. So this is basically the anatomy of this thing. So you declare types as usual, type, name. You just add this type parameter expression under square brackets, and then you have a base type. And here, the same for functions. The thing is, the most important part of this, like, of course, you have two parts. You have the name of your thing. You have the second part is the constraint. So talking about names, we tend to use some naming conventions for that. So usually we use like a single capital letter, like T from type. If you have only one, you tend to use like func T, any func T, another constraint. But you've seen examples like people using S for slice, E for element of slice or element of collection. But I tend to use the classic C++ style, which is you start with T and then follow the alphabet after that, T, U, V, and so on. For constraints is the new, I'd say probably the newest thing, like the most important, most foreign thing that was introduced to the language. But they are defined as interfaces. So this is cool. Like we can use the interface we have today. We can also use plain types, but this is more like, we're not actually using the type. We're just, if you only use the type, the Go compiler will wrap interface in that type. I'm going to show this in a moment. So we're using the interface of that type. And you can have these two special symbols. One is the tilde that says, I want anything that satisfies integer, and I'm going to go deep in the type chain to see if integer is the root of that type. Or you also have the bar, which is the union type. I say this could be an integer or a float 64. When you name your interfaces, we tend to use predicate form. Just like in traditional interface, we capture behavior, so we want to name them after verbs. Writer, reader, and so on. Here we want to name them as predicates like orderable, ordered, comparable, and so on. Like we want to describe what is constraining, what it is constraining. And we also have this alias, any, which is just a synonym for the empty interface, which matches anything, basically. So let's have a look. This is an example. So we're starting with the concrete. Hopefully it's readable for everyone. Concrete case first, sum of two integers. And we want to make this generic. So how do we do this? First we replace the type. And now we can have this like a type parameter, t. And let's use the constraint integer. This is the exact same function. So I'm saying I'm only allowing an integer to be there. And OK, let's say now I want to create my integer, which is an int, and I want to use, let's see, var I my int equals to 100, and I want to use var I here. So this will not satisfy the condition because I didn't say go to my base type, so I need to add this tilde operator to the definition of the constraint, and then I'm fine. So Then I can run, and then it will say, oh, my int. Now both of types were promoted to my int, if you look at it. And OK. As I was saying, this is actually syntactic sugar for this. Like, usually you would see something like this. This is the long form. So because it's not really the type, it's the interface of that type. If I say, no, I want to you know what? I want to support this with a float type. And you'll see that this, of course, is broken because I'm not, but I can extend this with the union and say float 64 and just run. And now I implement both types. Of course, this is a bit inconvenient to do this inline type here. So usually what you want to do is like say, oh, this is a number, and I have type number I actually can do this interface, and then I can run, and then you have your named interface as a constraint. That's everything you need to know about generics. I'm kidding. Actually, there's more, but it's good enough for this talk. Okay, monads. Who here know what a monad is? Oh, we have a few courageous people to raise their hands. I don't. That's why I didn't raise the hand. Monad from the Greek. This is probably not the right definition for this, but it was so cool I had to put it here. The elementary individual substances that reflect the order of the world and which from material properties are derived. How cool is that? It's brilliant, but unfortunately, it's not this definition we want. It's this one. A monad is a structure that combines program fragments, functions, and wraps the return value in a type with additional computation. Okay, now is the time I'll take a break and brief and say I have no idea what they're talking about. I'm going to give you a better definition. That's my definition. That's going to piss everyone that knows functional programming here, but for me, is that. It's a container of one element, and that's it. That's the definition. That's the important stuff. So why should I care about writing code for a container of one element? If you're trying to solve a problem, you don't start with the big thing. So I want you to imagine, like it will be an exercise of abstraction here now, that everything we're going to do here, if we prove that it works, could be used for lists, for sequences, for queues, for decks, for anything, any collection of more than one element. But I want to solve this simple case first, which is easier, or apparently it is. And there are plenty of monads, but I picked one, which is called the option type. And an option type is something that can have a value or no value. So it's a container of 0 or 1. Like it's a container of up to one element. And because this is heavily inspired by Scala, Scala uses the name for the container that has something, sum of t, and the container that doesn't have anything is none, that has no value. And theoretically, none also doesn't have a type, because you have nothing in it, right? Why should I care about this kind of thing? In functional programming, we use this to do, among other things, the concept of lifting. And imagine this function. I'm dividing a number x by y. The domain of this function is y different than 0, because you can't divide by 0. You have a panic, in this case, if it is go. So you can give all numbers except 0. So this function is only defined for y different than 0, or is not defined for y equals to 0. When you lift a function, we want to, of course, writing a idiomatic, more idiomatic form, this would, in Go, you have like the possibility of returning an error if you pass the invalid domain, like in this case, 0. Lifting a function is creating a function that can't fail. So in this case, the second function here, it returns an option of int. So, and in this case, for when it's not defined, it returns none. That's the change. So you don't fail anymore. It's safe. So this is an example. So you have the same thing, a partial division here, that if equals to 0, I return a divide by 0 error to avoid the panic. Then here is safe to divide. And the full function. This is a partial function. So the full function is the one that extends the domain. So then I return the option. And so I can call this safely in main, and this will never fail. This will just print nothing, basically. OK. I got this code from yesterday. I was at Bill Kenny workshop. I don't know if everyone who had the opportunity you had. Why should you care about not failing? As Bill Kenny said, I love this code. Any problem you solve with code is a data transformation problem. If you ever worked with functional programming before, we love to do this kind of thing. Data transformation pipeline. So you take an option, oh yeah, I need to do, I like to say that we beat the data until it confesses. So we just keep transforming until we get something out of it. So I'm filtering this, I'm applying a map, I'm doing operation, blah, blah, blah. And this code actually doesn't compile, but we'll see a version that does compile in a moment. But this, again, for a container of one is not super exciting, but imagine this is a list with a, I don't know, infinite amount of numbers, then you can see the benefit. And that's how, actually, Scala does processing. And Martin Odersky, who's the creator of Scala, when he talks about Spark, Apache Spark, which is a framework for data processing, he calls, oh, this is Spark Scala collection on steroids. Basically, when you take a collection that you can do parallel processing, and then further you can parallel processing multiple machines. So imagine we already have the facilities of Go routines with Go. Imagine if you could implement a parallel map here. Then you can just have like a simple line of code doing all the groundwork for you. That would be the dream. OK, can we do this in Go? This is uncanny valley territory now. First, let's define a simple API for our monad type or option type. New, so we can create wrap the value v in an option type, which will be sum in this case. We usually have this function is defined that helps us to see, oh, is this sum or none? A filter operation that will apply a function f, and if the filter is false or the thing is none, it will return none. A mapping transformation that will transform that option based on a function f, and that also map applies to none and is always none. And also, and finally, a for each function that just applies a function if it is defined, or if it's not defined, doesn't do anything. A few design considerations for this exercise. First, we don't want mutable state. We're not mutating the option. We are creating a new option. We don't need to use pointers. That's the actually, you should only use pointers when you need to. In this case, we don't. Then, when I was thinking about this, I say, you know what? Option. What is option? Is it a behavior? Is it an interface? Or is it a concrete thing? Is it a struct? So I decided to explore both fast, and we'll see how it goes. Then we're going to talk a little bit how to implement none. There isn't much to talk about this idea of, I was infatuated with this idea of none having no type. Is this possible? Maybe. And how do we handle errors if we are simply ignoring the errors? Option is not the best monad for that. But we'll see. There are other monads that can give you more options to treat errors. OK, so I start with this. Option is interface. Here I omitted get just for the sake of fitting in a slide. So we have is defined. We have filter that returns an option, applies the function, returns option. We have map, and we have for each. And here I hit the first problem, because this code doesn't compile, because we can't have type parameters on a method. We can only have type parameters in the definition of the type. So if I'm thinking about an option that I want to be able to apply any function that operates on my type and transform to something else, this is a huge constraint. I don't know the type yet. So I have a second type. Would promote, one of the alternatives is taking this u and promoting to the definition of the option itself. But then I'm hard coding and saying, OK, this option only works from int to string and nothing else. So this is also not a very good API. What I decide to do is to make map as a standalone function. So map is a generic function that takes an argument. The first argument is an option, and then applies any function you can think of. This is a more sensible, of course, I lose the benefit of chaining map to map to map to map, but okay, it's not beautiful, but it works. That's what I can do. But I decide to add the implementation we're going to see later is the special case map from T to T. Yes, that one I can have in my type. So, and this is, let's see how this works in the code. Hopefully it's readable. So again, here in this example, I didn't implement map, but we have the options. And so we have a new function. The new just returns sum because if I just need none, I can just use the 0 value. I don't need to use new for that. So sum is a struct that takes a value. That could be any. I have the get method. And here's some cool stuff that I thought about this example was worthwhile, because sometimes you don't use the type parameter, you can just ignore it. So you can use the blank, like the underline, should just simply say, oh yeah, I don't need this. I know that for sum is defined will always return true. And filter, basically I apply the function and return itself if the filter is true. Otherwise, I just return none. And because I'm returning optional, so I need both sum and none to implement this interface, basically. And that's how interface works. The implementation of none is quite simple. And you can see that even in the definition of none, I can ignore. I'm not using the type anywhere, so I'm just putting a placeholder here. I'm not using a none, I can ignore. I only use the type. And get, of course, get in none doesn't mean anything, but I'm using this syntax to get the 0 value of the type. But the caller should be careful enough to call isDefine first to check if that value is valid or not. Filter, there's nothing to do because this is none. I just return myself. And for each is even simpler. It's nothing. I don't do anything. I'm not calling the function. This is an implementation of the helper function map. The first thing I need to do is call isDefine. If it's defined, I just I apply the function f to the value of my option. If it's not defined, I just return none. And here, a very simple example application. So we have just creating a type, an option type from a number, and I call for each, and I define this print helper function that just prints the value. And you see, in example 1, it prints because this is defined. This is a number, is defined. I didn't apply any filters. Then example 2, I declare this lambda function that is even. And of course, 13337 is not even, so the filter will fail. Then when I try to apply for each, it won't print anything because it will apply to none. And the third option is I'm taking like the standard library string to integer to ASCII and applying for each and printing the string. Of course, I didn't need to do this. Of course, one of the main limitations of this is that I can't do simple things like println directly because it doesn't match the signature. It will complain that, oh yeah, this is a println is a variadic function that doesn't match the signature. That's why I need to do this kind of magic here to, I can highlight anything. That's why I defined this helper function, because I needed something that was not variadic to match my for each implementation. I think the beautiful thing here is that you can see that I can call for each, I can call map. Even though they are generic, I don't need to define the types. The compiler is smart enough to do type inference for me. There are situations where it is not smart enough, and in this case, in print here, if I just remove this int, because here, print is actually returning a function that I can call later that takes an argument, and we will just call println for me. Because at this line here, it doesn't know it needs to convert an integer yet. I need to give it the type parameter. It can't infer in this case. Oh, I have now broken two things. Let's just full, just for the sake of this. I broke too many things. But yeah, you see, I cannot infer t. So you will find situations where the compiler can't deduce the type, but most of the time it does a pretty good job. So in this case, if I add the type here again, it should work. And yeah, in this line as well. Okay, cool. This is the interface implementation. I'm not happy with it, and why? Because if you work with Go long enough, you know it's not a very good idea to return interfaces. We like to work in the concrete. Also something that Bill Kenyon said yesterday. We like to work in the concrete. Concrete is simple to reason. It's easier to understand, easier to read. So I was not super happy. Another thing I was not happy with this implementation is that because I have a very close definition. I have some and none. I don't want to have anything else. But if you define an interface, you can see you're basically saying, oh, I'm defining this behavior. I could have, I don't know, anything else that also implements this. So I felt I was leaving it way too open. Then I realized, okay, well, what if option is a struct? And this way, it simplifies much more the implementation. So I just have a type, a value of type t, and have a flag that saying that it's defined or not. And then now, I have less code to write because I don't need to implement some and none as two different types. I can return concrete things, and the zero value is useful. Basically, my zero value of my option type is none. And this is the result. So now we have this option value and define. When I created it, I create based on a value, so it's always defined. That's why define is true. If I want to just use the none, I just use the option as it is. I don't need to create with new. So is defined is just return define, get just to return the value. Filter, I check if it's defined first. If it's not, return none. So this is equivalent to none here. Or not, then if it is defined, then I call the function to filter and then return my thing. And for each, it's the same thing. I just check, is defined, okay, call the function. This is the special case for a map from T to T, just to have a convenience to change operations. I also added a few other things here that usually when you, we're going to talk this in a bit, when you want to, okay, this fail. Once you have none in your chain, none will propagate until the end. And then you can have at the end of your chain or else as an operation to say, okay, this failed, so I want to replace with the default value or do something else. So this is kind of the idiom here. This operates on none, so, or else, if it's defined, it returns self. If it's not defined, it returns something else, and this is the way you provide the default value. And also, we have get or else is the way of saying, oh, I want to get the value from this, but if it's not defined, if it's none, give me something else. The implementation of map is not much different than the previous one. Actually, I didn't change anything, just not even the types. And the application, the code from the example application is exactly the same, and you can see that hopefully it will work. Let's just run this. So you see, it's the exact same code, but the benefit now is that we have concrete types, and there's less effort to write. So we can have map, apply a standard library function, call for each. In this case, my operation is just printing, and I have 1 and 3 because they are defined. 2 is not doing anything because is even returns false. Okay, so this is this works so far. Then the question was, can we have typeless none? No, we can't. Because if we're using the interface implementation, how can we implement get? We can't, because I can't not return a type. And in the struct implementation, the type is already there, so you can't do anything about it. So yeah, no, that was kind of a no-brainer. Kind of disappointing, right? Error handling, I already covered a little bit of this. So usually in options, you use like the or else or get or else type of function, or you also sometimes you have or new if you want to have like a pointer semantics. And in this case, like if I filter, oh, it's not upper, then you print like not upper because or else says this. It's pretty straightforward. You saw the implementation, not anything special. In other options, like sometimes you have an option called try, which returns success or failure, or this could also be futures, could be like a type of monad that says success or failure. So you can have other type of function, on failure, on success, do blah, blah, blah. Let's go back to lifting. So this, remember, lifting was the idea of, how can I extend the domain of this function to work with some, like in a way that doesn't fail? Like, and the idea is to, if we have the option type, now we can have it return none instead of return an error. But the problem with this, and this is where Go kind of doesn't help us too much, is that there is no easy way to know if a function is defined. The only way we know is calling it, see if it fails or not. If you have, like in Scala, for example, it has the compiler is smart enough to analyze some code paths, and they'll say, and you'll provide you a magical is-defined function that you can call and say, oh, this is not defined on 0, so this is a partial function. The Go compiler doesn't provide us this, so, but we can kind of fake this by actually calling the function. The benefit in language like Scala is that you don't need to call the function for it to fail to see it's not defined. But in this case, we don't have much of choice unless you want to re-implement everything. And the idea is I was playing with is, and that's why I missed the speaker dinner yesterday because I was trying to implement lift, is can we do lift for any function? Because manually, me rewriting every single partial function in a full function is kind of annoying. And actually, it is possible. It's a bit tricky. So here's an example. I did like an option lift, ASCII to int. And you see that the output is, okay, in this case, I can't convert to integer, so it will return none. My full function will return none. And the 1, 2, 3, I can convert, so it returns some. So how does this work? And let's prove that this works first. So if I run the example, yeah, it will pass the test. If you're not familiar with example, this is something I love to go. It's really hard to find how to write examples because if you Google example, you'll find anything except what you want. So here I'm lifting the standard library function that takes a string, returns an int and an error, to a full function. You see there's some magic there that I call this full is a function 1 that takes string and an int. And you see, oh, it doesn't take a string and an int. Actually, it does. The way to read this is that the string is the argument, int is the return value. So a function 1 means a function with one argument and the return value of int. And this is some black magic that we're going to do. I stole this from Scala. Scala does the same. Basically, I have a bunch of definitions here. Let's say I have a bunch of partial function definition. Partial function 1 has one argument, returns error, returns the result and an error. Partial function 2 takes 2 arguments, returns a result and an error. Partial function 3 takes 3 arguments, returns a result and an error, and so on. And I created the equivalent full function definition for all of them. And if you think function 1 to 3 and define types like this is crazy, if you ever work with syscalls, we have syscall, syscall 6, syscall 9. And if you ever wonder what's the 6 and the 9 about, yes, it's the number of arguments. And this is not crazy, actually. If you look at Scala, Scala defines function 22. Everyone from 1 to 22, that's the way. The compiler does a bit of magic to hide this from you. In Go, we're not so lucky, but we can do it. So what I did with lift, in this case, so lift, if I don't say any number, it just lifts a partial function 1 to a function 1, which means I just need to call f with my list of arguments. I have, let's close this. Then define lift 2, that takes a partial, you already know the pattern here, that returns a full function 2. I call the two arguments, and so on. Where Go doesn't help us is that there's no way to define. To be honest, I only care about return value, but there's no way to write, like to express that. You say, you know what, just replace the return value for me. I want to accept any function with any number of arguments. I try experimenting with variadic functions, then you need to convert a function 1, function 2, function 3 to a variadic one. Not beautiful as well. So in the end, this was the best thing I could come up with. So I have lift, that basically lifts 1, and I have lift 2 and lift 3. So in this case, lift 2, I'm using parse float. It takes 2 arguments. They're all different types. But the beauty of this is that type inference works for us. So this it's still kind of clean. I need to call lift 1, lift 2, lift 3. But you see it converts properly for the things I want to do. And yeah, you have non-float, some float. Lift 3 here, parsing takes 3 arguments. Also I can. But the sad part is that I need to call the function. I can't just call is f defined, then return option none. That's where the compiler doesn't help us. Okay, cool. So almost to the end. Conclusions. Go is not Scala, apparently. The lack of type parameters on methods limits the creation of fully ergonomic options. I had to use the word ergonomic. I thought it was so cool. But we can get away with creating standalone methods, and this won't be such a bad interface. Definitely go for structs. If you look at this code, I made this package. Don't use in production, but I decided to opt for the struct implementation as the canon one. Yeah, option types are fun thought exercise. This could be extended to implementing lists, implementing maps, implementing sets, or whatever you can think of, making like this more functional approach. But it's hard to tell if this ever will be production ready because of the kind of support we need from the compiler is not there yet. A bunch of references, and yeah, these are my contacts. If you want to follow me on the That Bird app, if you have took any pictures from this talk, please share, tweet me and at me. And that's it. Any questions?